Okay, goodbye. Hello, in this video we're going to be talking about the derivative. It is a very important concept for calculus. Uh, we've talked about the average rate of change, which is basically slope. We want to try to find the slope of a curve. That is where the derivative comes in and the instantaneous rate of change. This is the definition of a derivative. We want to use this thing in order to figure out what the derivative formula is for a function. So let's do precisely that. I've got this function f of x equals x squared minus 5. I want to figure out what is the derivative of this function. In order to do that, I need to find the limit. The limit I'm looking for is f prime of x, so I need to start with what f of x plus h is. So I need to put an x plus h where that x is in my function. So right here on that x, we get x plus h squared minus 5. So I'm just kind of continuing on with that thing. So I've done that piece. Then I've got this piece minus whatever f of x is. So that's just our straight function as is. So minus x squared minus 5. I'm going to wrap that up in some parentheses. I'm going to extend my line. Now my job is to just evaluate this limit, and I'll have my derivative. However, I can't plug in h right now because I've got an h in the denominator. It's just an h there. So I've got to simplify that numerator, see what's going on there. I'm going to square that x plus h. So that's x squared. And then this bit becomes a plus x squared. No, not plus, minus. Excuse me. Minus x squared plus 5. This is still the limit. This is still all over h. And it is still equal to f prime of x. All right. Well, now what can we simplify? Well, this x squared will cancel, will zero out with this x squared. This minus 5 will zero out with that minus 5. And so then we're just left with that 2xh plus h squared over h. Cool. Now you might say, hey, we can cancel. So we can cancel this h with that h and turn that into just a regular old h. So this is the limit as h approaches 0 of 2x plus h. Well, then now we can direct substitute. So f prime of x da 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 is just 2x after you direct substitute in that 0. So our derivative is 2x. Neato! We found it. That'll tell us the slope at a single point anywhere on our original function up top. How cool. Something to know about notation. There are a lot of different times and reasons that mathematicians will use different notation for derivative. I need you to know that all of these mean the same thing. We just did this one with the h approaching 0. There is like kind of the old-fashioned way of talking about it was this delta x instead of an h. Finally, this one down here is still a derivative. However, this one is looking at a single point rather than the derivative on the whole slope. In this example, it'd be tricky to figure out the derivative everywhere, but fortunately, we only need to figure out the derivative at -2. So we can use this form in order to be able to figure out the derivative at that single point. So f prime of, we want to check it at -2, will be the limit as x is approaching -2 of, we need f of x, so that is just going to be our straight just f of x. Note that I'm not substituting quite yet. Minus, I need to do what f of c is. So I'm actually going to do that off to the side. So f of -2 will equal -2 cubed, which is -8. And then 2, that'll be +8 plus 1. So that is just 1. In the denominator, we have an x minus our c, which is -2, so we'll have x plus 2. So how's our limit looking? We got the limit of, well, now we just have x cubed plus 2x in our numerator over x plus 2. All right. I can't direct substitute because I'd have a 0 in the denominator, but I think I can factor cancel. So I'm going to factor that numerator and bop, bop, factor cancel. I forgot my limit. So this equals the limit as x is approaching -2 of x squared. And now we can direct substitute that. So f prime of -2 will equal -2 squared, which is 4. So there is our derivative at 4. No, at -2. The slope is going to be 4. All right. In this example, I've actually gone through all the steps because I really want to get to this part where I'm trying to find my limit and I want to think about what's going on here. I can't evaluate this limit, but I can think about what's happening as I approach on either side. And a great way to see it is in this Desmos tool that I posted at the beginning. So as we come in, the derivative is this red line. That is the slope of that line, that tangent line. So as we come in closer, you can see how I have this negative slope. And as I get close towards 0, I'm getting more and more negative. So it is definitely a negative slope. At 0, you can see it just completely disappears. And then right afterwards, I'm suddenly a positive number. So I've gone from a very big negative number to a very big positive number. So that's not cool. That's not cool with limits that we're not approaching that same slope on either side. So at this point, this function is not differentiable. That slope is changing too rapidly at this point. In this example, again, I've gone through the steps, I've gotten down to this bottom part, and this is an example where we would have an infinite discontinuity. But what does that mean in terms of the derivative? Well, again, I've typed it into this thing, and you can see as we're approaching, we are like, there. We're at a very deep negative number, so it is heading towards negative infinity. And as we cross to the other side, we are still at a very deep negative infinity. So you might say, hey, well, we're heading towards the same thing. So it's negative infinity, negative infinity. Why can't we be differentiable? Think about the idea of a differentiable in a tangent line. A tangent line is bouncing off the graph at a single point. At that point, at 6, there is no point. There's no point for us to bounce off of. So if we can't bounce off anything for that slope of our tangent line, then we can't be differentiable because there's nothing to like ping ourselves off. And there's nothing there. So ends our video on the derivative. Derivative is related to the average rate of change, but instead of doing 2 points that are far apart, it finds the slope at a single point. It is the slope of the tangent line at that single point. Make sure you've written this down somewhere. I've been saying it, but it's nice to write it down somewhere. We can also find the derivative at a single point using this alternative form of that derivative. Thank you for watching and a good derivative. Bye.